Welcome back to the meanwhile sixth installment in the never-ending series about making sense of NMEA 0183 sentences. Links to the previous installments down in the description. We've written almost 2,000 lines of code so far, so it's again high time to do some housekeeping. That is splitting that one big file into several files, header files and CPP files, meaning going slowly but surely into the direction of making that a real library. I want that library not only to compile in the Arduino environment, but I want it also to be able to compile in a PC environment, that is Windows or Linux. And I want this library to be truly extensible, which it isn't at the moment. So there's a lot of work to do. I don't know if I will cover everything in this single video. We'll see how far we get. Enjoy! Let's start by splitting the whole thing into different header and CPP files. But before we have a look at what I did, I have to make a confession. I renamed a whole lot of the classes. That's something you have to get used to because I tend to do that a lot during a development process. So, the names of our top-level classes, NMEA Codec, NMEA Codec Proprietary, and NMEA Codec Parametric, not shown here, remain the same. But here for the proprietary stuff below that, you see here my scribble. I wasn't happy with that. So, in the last version, code version 11, below that comes the NMEA Codec Manufacturer and then NMEA Codec Manufacturer XXX for a specific manufacturer, and each specific manufacturer has its message handlers, which were called NMEA Codec Manufacturer XXX Message, and for specific message NMEA Codec Manufacturer XXX Message YYY, which was far too long and cumbersome. So for the proprietary stuff, I came up with that naming scheme here. And the idea is, as you go down one level, you simply delete the first word here in the identifier. So below the NMEA Codec Proprietary now come the NMEA Proprietary Manufacturer without the codec, respectively the NMEA Proprietary Manufacturer MMM. Yeah, the manufacturer code for a specific manufacturer. And below that, dropping the proprietary, we have the NMEA Manufacturer MMM sentence base class, and then the NMEA Manufacturer MMM sentence SSS, so the sentence identifier of the manufacturer derived classes. A lot shorter here and a lot more concise here. I did something similar to the NMEA Codec Parametric stuff. As mentioned, that class keeps its name, but below that we already had that convention that I deleted the first word here, so the codec is missing here, and they all started with NMEA Parametric. And the base class was called NMEA Parametric Fields Handler, and the derived classes NMEA Parametric Fields Handler XXX. And I renamed them to NMEA Parametric Sentence, respectively NMEA Parametric Sentence XXX. A lot shorter and a lot more object-oriented because these classes are really handling specific sentences. Now, let's have a look how I split our code into different files. So we still have our main file here, so NMEA 0183 version 12. Then I have here an NMEA 0183 Arduino CPP. That contains all the Arduino specific code. Remember, I want to make that library portable. And associated with that, we have, of course, an NMEA 0183 Arduino H header file. Then we have the NMEA 0183 Core CPP, which contains all the, hopefully in the future, portable core functionality of the library, and an NMEA 0183 Core H header file for that. Now I'm temporarily staring at you from the middle of the screen because I want to show you just in case you've never done that before, how you can create more tabs or files in an Arduino sketch. You do that via that menu here on the right where you find New Tab. And if you click that, it asks you for a file name, for example, xyz.cpp. And then you click OK, and you have another tab here for another file in your sketch. Let's go over these 4 new files in a little bit more detail. And I'm not talking about a code walkthrough here, because creating these files was mostly copying and pasting from our main file and then separating the class definitions from the class implementations plus the renaming stuff we already talked about. I'm starting a bit backwards here with the NMEA 0183 Arduino H file, which contains the class definitions for Arduino specific stuff. That is our class NMEA listener hardware serial and our class NMEA talker hardware serial, because you know hardware serial is very Arduino specific. 2 remarks here. If you are using Arduino specific stuff like hardware serial or Arduino specific types like Boolean in one of these additional tabs here, you do have to include Arduino.h. And if you want to include other .h files from your sketch here, which are defined here in the tabs, you have to put the name of that file here in hyphens, not in brackets. Otherwise, the Arduino IDE won't find them, because if you put them here in brackets, the Arduino IDE will look for the file within the library directories. Also, that's basically a C++ respectively C convention. You start your .h files always with an if not def preprocessor statement, checking if a macro that is usually closely related to your .h file name, in our case NMEA 0183 Arduino_H, is not defined. Only if that macro is not defined, we actually include the stuff between the if not def and the hopefully added at the end of the file and if preprocessor statement. And after that, we define that macro. That prevents the stuff between the if not def and the end if to be included multiple times and thus causing compiler errors. A quick peek at the NMEA 0183 Arduino CPP file, where we of course include the NMEA 0183 Arduino.h header file, and we implement our 2 classes. So the NMEA listener hardware serial and the NMEA talker hardware serial. That's it. Then we have the NMEA 0183 core.h containing all the type defs and class definitions for the rest of our NMEA functionality. And same game here with the if, not def and define. And we also have to include the Arduino.h here again, because I'm still using such evil that is Arduino specific types like byte and Boolean. If we want to make that part of the library really portable, we have to get rid of that at some point. Finally, there's the NMEA 0183 core.cpp, which implements all the methods of the classes defined in our NMEA 0183 core.h. There's not much left in the main file of our sketch, the NMEA 0183 version 12. Of course, we include here now the NMEA 0183 core.h and Arduino.h. And we still have, from that point on, it's pretty much unchanged compared to the version V11. Our parametric sentence array, we now have here new class names. So these are now all called NMEA parametric sentence. And we have further down still our manufacturer codec array, also with new class names here. And finally, we initialize our codec and our listener, and from there on, it's completely unchanged. One thing I want to point out here is if we compile our version v12, we need 17,066 bytes of flash memory and 557 bytes of RAM. Our previous version, v11, which is code-wise exactly the same, but for the fact that we renamed some classes, needs 17,186 bytes of flash memory, so 100 bytes more. I don't know why. And exactly the same amount of 557 bytes of RAM. So you see, splitting your sketch into several files costs you absolutely nothing, and it makes things much more manageable. And the new version 12 does exactly the same like the previous version 11. Yeah, I have no reception here because I have my GPS module here right beside the notebook and not at the window. But you can see the output is exactly the same. Okay, let's talk now about extensibility. So what do I mean by the library should be extensible? And we will focus for now on the NMEA parametric sentences, and I'm here again within the NMEA 0183 core.h header file. Currently, the library implements a handful of these NMEA parametric sentences. And as you know, there are over 100 of them. So the time might never come when the library implements each and every one. So the need might arise that without touching the library, I want to add new sentence types within my own code using just the framework of the library. And just looking at the classes in the library, that's really simple. I mean, I just have to derive a new class from my base class NMEA parametric sentences. However, if we scroll a little bit up in the file, we find something like that enum class NMEA parametric field types. And obviously, I cannot extend that type in my own code with new sentence types. Also, within the struct NMEA parametric fields, I not only have that NMEA parametric fields type, but I also have a union containing all the structs for the different message types. And this I also cannot extend in my own code. There are several good reasons to use a union here, and I talk about them in part 1. Card here, link in the description. But now the union is biting us in the behind. Okay, so the union has to go. The problem with this enum type is relatively easily solved. We just, don't use an enum anymore. We just define that here as an unsigned integer and we're fine. To demonstrate how I arrived at a solution for our union problem, I want to fall back on some really simple demo code here that is kind of mock-up of what our library does. If I showed you the finished solution in the library code itself, it would be quite overwhelming because it's getting ugly, like C++ ugly. We will develop this demo code in several steps until we get it right. So we're starting here with Extensibility 1. And please note the comment here, this sketch does not compile. It just shows the direction in which we want to go. So let's dive in. I have here two structs, sentence 1 and sentence 2, which are the equivalent to our NMEA sentence structs in the library. The first one contains a char field and the second one contains a little string field. What's new here is that these structs are derived from a base struct sentence, which is empty. Then we have a struct data, which is equivalent to the next higher level in our struct hierarchy in the library. And it contains, of course, a type, a sentence type. I didn't bother to define a num here. And just one other member, and that is our struct sentence. Basically, we replaced our union of structs with an object that is of the base class of all our structs. At this point, I should mention, just in case you're not familiar with the fact that structs and classes in C++ are, broadly speaking, the same, okay? There are subtle differences that are more on the semantic side, but what you can do with a class, you can do with a struct and vice versa. Anyways, like in the library, we have a decode function here, which is very simple. In our mockup, it just gets a sentence type and some string. We have a local data variable, yeah, exactly the same like in the library. And we switch according to the sentence type. If it's 1, then our sentence type inside data will be 1. If it's 2, our sentence type inside data will be 2. If it's 1, our sentence inside the data struct will be derived from the decode1 function, and for 2 from the decode2 function. And at the end, we return our data struct. Our functions decode1 and decode2 are very short and primitive. Both return a sentence, so our base class, and both get a string as an argument. So in decode1 we have a local variable sentence1, of course, and we fill here the field1 with the first char in our string, and then we return our sentence1. In decode2 we have, of course, a sentence2 local variable, and we do a string copy of the incoming string into our field2, and then we return sentence2. Simple. Like in the library, we have a print function that gets as argument a data struct. And to make things very transparent, I have 3 local variables here. So a sentence1 struct, sentence2, and the base sentence struct. First, I extract from our data struct the sentence, and then I switch according to the sentence type. And if the type is 1, I try to extract with a cast the sentence1 struct from the sentence, and then I print out that field 1. If it's type 2, then I try to extract the sentence2 struct by casting to sentence2 our sentence struct and print out the string field in it. Nothing surprising in the setup, just initializing our serial interface and waiting until it's ready. In the loop, I have 4 data structs here, which I called data1a, data1b, data2aa, and data2bb. You will see later on why. I do a serial print test, and then I fill my data1 with a decode of type 1 and string A, my data1b with decode 1 string B, 2AA with 2AA, and 2BB with 2BB. And afterwards I print out all my 4 structs, and then I just do a new line and wait 250 milliseconds. This code is of course easily extendable with new sentence type. I just have to add here a new struct sentence 3, which I derive from a sentence, and then I give it a field integer, field 3, whatever. Doesn't really matter, okay? There's only one problem. It does not compute, that is compile. The core problem is that we cannot cast our base struct to the derived struct. Please note, the other way around, it's absolutely possible. You can always cast from your derived struct to the base struct. We do that implicitly here. The reason why is also easy to see. A sentence simply contains nothing, so we cannot derive from that the information contained in sentence 1. The same holds true for classes, of course. The solution to the problem is, instead of using structs, using pointers to structs. Very similar to what we did here in our array of handler classes. Yeah, that's an array of pointers to the base class of all handler classes. A little errata at that point. When I explained that array here in part 3, card here, link in the description, my wording was obviously not very concise. Big thank you to Mike Lopez pointing that out to me in the comments. So yeah, regarding the virtual function overrides of the virtual function in the base class, go for the comment here and not what I said in the video. Anyway, let's continue. So all we have to do is to change within our struct data the sentence from being a struct sentence to being a pointer to a struct sentence. There's absolutely no change within the decode function. There are some subtle changes within the decode1 and decode2 function here. First of all, they now return a pointer to a sentence struct. Then the sentence1, respectively sentence2 local variables here are now static, meaning they survive somewhere in the memory when we exit the functions here. And also both now return a pointer to their local variables and not the local variables themselves. Our print data function got much shorter because we can now simply cast our pointer to a sentence struct to a pointer to a sentence1, respectively pointer to a sentence2 struct, yeah, depending on the sentence type in our case statement, and then access field 1 and field 2 respectively. And this code compiles without any problems. Now, before we have a look at the serial monitor, at the output, I wanted to point out again that in the loop, I decode here 2 sentence1 objects, one after the other, and then 2 sentence2 objects, one after the other. One with the fields AB field content and the other with the field content AABB. Now, serial monitor. And most of you probably predicted that, but we only get the data for our last decoded sentence1, respectively last decoded sentence 2 here. Yeah, the data from the previous decodes get somehow overwritten. The culprits here are, of course, the static variables in our decode functions. I said they survive the exit of the function, but they only exist once in the memory. So each time you enter the function, they are reused, and that means they are overwritten with the new values we are decoding here. So in our next version, that's version 3 already, we no longer have here static variables, but instead we have pointers to the structs. And we need to add another statement here, and that is a new statement. So our pointers will point to an actual struct, and we just return that pointer now. Of course, we have now here within our decode code to handle our sentence1, sentence2 as pointers to structs and no longer as the structs themselves. In the loop, I also print out now the free memory, that is the remaining RAM we have. I don't want to get into a tangent about that free memory function. Let's just say it comes from a library, okay? And it's very important to check that because of our new statements here. That is, we are allocating memory each time we call our decode functions. And if we don't release that memory again, as I do here now with these delete operations, then our memory shrinks and shrinks and shrinks until the whole thing crashes. And looking at the serial monitor, everything's fine. So our free memory stays at 5920 bytes and our decoding works perfectly. And we could leave it at that. I mean, our data structure is now easily extendable. I could simply create here another struct sentence type 3 with an integer field 3. And of course, in the real code, I won't have to extend the switch statements. We use our array of objects to handle that. However, I do not like that I have to care of the delete stuff here. I would very much like the library to take care of the memory management. At first glance, that seems simple. Just add to our struct data and destructor, which deletes the sentence. And yeah, while we're at it, we also can add a constructor which sets the sentence type to 0 and makes sure sentence is really a null pointer. So when we enter the loop, the constructors for our data structs here are called. Everything is nicely initialized, and when we exit the loop, the destructors are automatically called for all our data structs, and the delete operations are carried out for the sentences. By the way, the delete operation is really intelligent. So you can call it with a null pointer and then it will simply do nothing. And it doesn't care if the sentence pointer here is pointing to the base struct or to one of the derived structs. It will work in each case. There's only one problem here. Well, basically there are two problems, but yeah, one after the other. And that is we are using the assignment operator here to assign a struct to another struct. So what's the problem with the assignment operator? Well, we have our struct data here that contains a byte type and a pointer to a sentence. And I abbreviated sentence type to type here. Now let's assume we have two of these structs here declared, data A and data B, and we do an A equal B. So what does the compiler do with that assignment operator here? By default, it will translate that to an A type equals B type and A sentence equals B sentence. So it does an assignment operation for each member of the struct. So if B type was equal 1 in the beginning, then after the operation has finished, A type will be equal 1. And if B sentence was pointing to some sentence 1, because we have type 1 here, in the memory, then after the operation A sentence A will point to the same sentence 1 here in the memory. And what happens now if the destructor for data B is called and this ceases to exist? Well, then our A sentence is pointing into the nirvana. And indeed, the destructor for the right side of our assignments here is called immediately after the assignment operation finishes. And that happens, of course, here in our decode function, where we have our local variable data, and then we return data, and then we exit the function. So after exiting the function, the destructor for this data will be called. And, well, as a result, the sentence pointers in our data structs here are all pointing to nothing. To solve this problem, we have to override the default assignment operator for our data structs. There are some rules you absolutely must and some rules you should heed when you override an assignment operator. So the first rule is only perform action on non-self-assignment. So if you write something like A equals A, absolutely nothing should happen. And this if statement ensures that. So this is this, This is the left side of our assignment operator, and here I called it assigned. That's the right side of our assignment operator. And only if these two are two different objects in memory, so we're comparing here pointer addresses, then, only then, we do something. Second, you should, if possible, reuse resources. So I'm checking here if the sentence types on our left and our right side are actually different. Only when they are different, I delete the sentence on the left side. And if the assigned right side sentence is not a null pointer, then I change that pointer here on the left side of the assignment operator to a new sentence. We will talk about this new in a second. Otherwise, yeah, if we have a null pointer on the right side, then of course we also have a null pointer on the left side. And at the very end, I do the sentence type assignment here. And then finally, if we're not handling here a null pointer to a sentence, I do a sentence copy here, and we will have a close look at that copy here also in a second. And afterwards, because it's an assignment operator and it's C, and the result of an assignment is also, if you put it in brackets, visible outside, we return, this. So the left side of the assignment. Now, let's talk about the new and copy methods. They are defined as virtual functions here in my struct sentence, and they have no implementation in my struct sentence, making sentence a real virtual struct, so you cannot instantiate it. That forces my derived structs, sentence1 and sentence2, to actually implement these two functions, otherwise you couldn't instantiate them either. Anyway, in sentence 1, a new returns, of course, a new sentence 1, and in sentence 2, a new returns a new sentence 2. And copy in sentence 1 copies correctly cast the contents of a sentence 1. That is, in our case here, just that one field. While a copy here in sentence 2 also casts properly the pointers here and copies the member of sentence 2. Here applies, of course, the same principle we are already using in our array of sentence handlers. So depending on where a sentence pointer is actually pointing, so a sentence 1 or a sentence 2, the correct virtual function is called. Short remark at that point, I would have loved to call these methods just new. However, that's of course not possible in C++ because new is a reserved keyword. So I went with a new. And so in my assignment operator, if I call here a new, and this is, for example, pointing to a sentence 1, I get actually a new sentence 1. And if I do later on here a copy, and this is pointing to a sentence 1, I get the correct casts for copying the contents of a sentence 1. Let's summarize the most important points. So we've overwritten the default assignment operator for struct A. And our assignment operator does for the byte type exactly the same as the default assignment operator. However, it works for the sentence pointers different. So our assignment operator does first for the left side a sentence a new, creating a new sentence 1, if the type is 1 of course, inside the memory. And then it tells that sentence here to do a copy of this sentence, the sentence we are pointing on the right side of the assignment operator. And now what happens if that gets deleted? Nothing, because we're not pointing on that, we are pointing to a copy of it. So, problem solved. But I mentioned there's a second problem, and the second problem is exactly here, when we are passing a data struct by value to a function. Now, what exactly is happening if you have a function f and you pass a variable a of type t by value to it? Of course, you can use that variable in the function. But of course, that variable here is a local copy. Okay, we can do to it whatever we want. We won't change the a we passed here as an argument. So how does a compiler does that? You could imagine the compiler inserts some code like this. So a declaration for t, a local, so our local variable, and then simply an assignment operation, a local equal a argument. And we wouldn't have a problem. Unfortunately, that's not the code generated by the compiler. In fact, at that point, the compiler uses the copy constructor of a class or struct. So in our case here, t, a local is a copy of a argument. And keep in mind that the destructor for a local is called when we exit the function. So our sentence pointer would again point to the nirvana. So, to make things watertight, we also have to override the default copy constructor of our data struct. And in theory, you could reuse the assignment operator for that we already defined. However, that's generally discouraged. So instead we have here a watered down version of the code of the assignment operator. So first we do an assignment of the sentence type, and then if the sentence here is not a null pointer, we do the sentence anew and the sentence copy, and otherwise we set sentence to the null pointer. And finally, we no longer need at the end of our loop here the delete statements to delete the sentences in our data structs. And just in case you didn't believe that this code will work, here's the output on the serial monitor. So you see free memory stays exactly the same, no memory leak, and we have completely automated memory management. Okay, one more enhancement, then we're finished, I promise. So here in my data struct, I don't like that we still have that byte sentence type, because there's always the risk that the sentence type in the data struct gets out of sync with the sentence pointer. So for example, we have here sentence type 1 while sentence is pointing to a sentence 2. And this can be avoided. And we avoid this, and by the way, we are now at Extensibility 5, by simply deleting our sentence type. No, seriously. We introduce a new virtual function, type, in our struct sentence, and of course, type in sentence 1 returns 1 and type in sentence 2 returns 2. So we're always in sync. Now we add to our struct data a function type, and that function simply checks if the sentence is not a null pointer. If it's not a null pointer, we return this sentence type, and otherwise we return 0. Our constructor for the data struct is of course now simpler. It doesn't have to initialize sentence type. And also our copy constructor here gets simpler. We don't have to assign the sentence type anymore. And the same also holds true for the assignment operator, where sentence type simply the lines disappeared, and where we need the sentence type, we now use this type. The decode function got also simpler, so here is now the sentence type line missing in the case statement each time. And our print function, well, it doesn't get simpler, but we are using now here in the switch data type. Before we have a look at the serial monitor, I wanted to point out some changes I made to the loop. So I have a fifth data struct here, and I also have a sentence one pointer here, because I wanted to model another use case exactly here. You remember we manually construct an NMEA sentence for our proprietary sentence stuff, okay? And that's basically what I'm emulating here. So I say sentence one is a new sentence, and sentence one field one is C, and then I say data 1C sentence equals sentence. And I also print that out here, that data 1C struct. Maybe some enhancement in the future, but for now it doesn't look that bad. Now we have a look at the serial monitor. And it works as expected. I think free memory changed by 1 byte or so. I don't quite remember, but it stays constant. That's the main thing. And if you see here, yeah, sentence one type, field one equals C. So everything's perfect. That was your trip to C++ hell and back, brought to you by Robert Smorgasbord Travel. No, seriously, if, for example, a Smalltalk programmer would ever watch this video, he or she, we want to be politically correct, would probably laugh his or her behind off. Anyway, till next time, I will rewrite the library using the techniques we learned today. And we will do some performance measurements comparing, then the new library version with the old library version in terms of speed and memory usage. After that, we can finally tackle that portability issue, okay? Make the library really portable between different systems. Till then, bye.